Hi, everybody. It's St. Vincent St. Mary. My name's Dan, and I'm joined here today by Tara Ruttley, who's going to answer some of your questions. And like he said, we are sitting right now in the International Space Station Mission Control Room, and this is where all of the main console positions are for controlling the systems on board the station 24/7, 365 days a year. So, without further ado, if you guys want to go ahead and get started, Tara is very excited to take some of your questions.
Yeah, hey guys.
Uh,
I'm looking forward to talking with you today, and I'll give my best answers as possible. I think you guys have some pretty good questions planned, so give it a go.
okay, let's start with Scott. Introduce yourself and ask the question.
Hi, this is Scott, or Phil the Thrill. What innovations have come from space travel, and what innovations are expected to come from space travel?
Okay, what kind of innovations? Whew, boy, the list is a mile long, and even crossing my desk on a regular basis, they're just things still in pouring from Apollo. But some of the ones I think that you could relate to the most would be the NASA DeBakey heart valve. So, for example, that's a heart valve that's saved a lot of lives, developed based on the concept of a design that was used in a fuel pump for NASA vehicles. So that's something that we've taken just from NASA vehicle use all the way to how it gets inside of your heart. And Dr. DeBakey was instrumental in working with NASA on translating that. That's just one example. Right now, for space station, I think what you would find beneficial, it's something cool to know, is with our ongoing work up on station, what's in the works is a vaccine development for food poisoning for salmonella bacteria. And so, food poisoning, if you've ever had it, is awful. But not only does it make you miserable, it actually kills around the world thousands of folks. So we have found in space that bacteria and some viruses, some of them actually become more aggressive. And not quite sure what's causing it, but something about the microgravity environment. And so we've based on that and that aggression that's tuned up, we've been able to identify the genes responsible for that aggression. And when you know what's going on with a particular gene, you can manipulate it, manipulate the proteins that come from it. And so a commercial company has actually taken that data here and flown a couple of their own samples and found a way to create a vaccine targeting that specific gene against the food poisoning bacteria salmonella. So what you might potentially see is one day out of this, it's still in the works, these things take a while, is the vaccine development for food poisoning. So I know if it were to come out, I'd be the first in line, I think. It's an awful feeling to have ingested salmonella. But these things do take time. That's something you might not see for a few years as it's going through the FDA approval process now. But with regard to station, I think that's probably one of the big things to look out for.
Definitely worth it, too. Okay, why don't we move on to the next question?
Okay, we'll have Greg ask the question.
Hi, my name's Greg. I know I was just wondering, like, how do spacecraft like communicate with each other to make sure they don't cross paths? Considering that, like, I don't know, direction is kind of relative, because like there's no direction, I guess, in space, because we don't have the poles, so you don't have a compass. I don't know, how would you steer clear of other spacecraft out in space?
Yeah, that's a good question. So for NASA, we know where all of our vehicles are at all times, and this is controlled on different levels across these space agencies around the world. And the space agencies around the world communicate their launches and landings, and so at that level, we know what's going on with regard to space flight, whether it's a manned vehicle or not, and our satellites. Now, there's a different level, which is probably at the level of the Defense, Department of Defense, that we at NASA have less insight into, but we coordinate appropriately so that all the right agencies are all tuned in to the right place to make sure that these trajectories are not critical or threatening with regard to everything that we have on the maps up there. Now, with regard to space station vehicles visiting the space station, I know that we work regularly with our partners that are on space station, and that would be Russia and Europe and Japan. We all have manned and unmanned. Well, Russia has manned and unmanned vehicles. Japan and Europe have unmanned vehicles, and we all know when those are launching. We're all in tune with those, and so we plan around each other for those, because it's not just a matter of avoiding each other in space, but then we have to sometimes share docking ports when we get to space station too. So I hope that answered your question.
All right, next question.
Okay, let's have karate girl.
Hi, my name is Celeste. I was reading a little bit about your zero gravity research facility, and I thought it was really cool. So I was wondering if you could just kind of tell me about some of the experiments they do there.
So there are a couple of different, what I'd call analog rooms or facilities that are analogous to what you might experience in microgravity. And I'm not quite sure the one that you're reading about, but it may be that you're referring to the drop towers, in which you can take an experimental payload up hundreds of feet, either high into the sky or deep down into the earth it'll fall, and you can drop it over a period of maybe 5 seconds. And then with that drop, that's simulating what you would experience in microgravity, because that's just really free fall. And the types of investigations I think that are good for this are combustion experiments, where you can light a flame and just investigate what's happening with that flame structure in a short amount of time. Even fluid physics experiments are good for that. So I think any of the basic fluid type or gaseous type experiments would be really good for that use. The human physiological experiments obviously wouldn't be good for that, because drop towers just use a package of hardware that you just drop. Now, if you are referring to the airplane, there are parabolic airplanes that fly a series of parabolic arcs over the Gulf of Mexico. We have one here in Houston, and I believe there's another one in Germany, where you get about 30 seconds. Once you're at the top of that parabola, you get about 30 seconds of actual microgravity. And that's when you can activate your investigation. So it's a little bit more, it gives you a little bit more time than the drop towers, and it's probably more useful. I've seen some human physiology experiments that have been able to be performed in those kind of situations, particularly with regard to exercise type experiments, and just taking, looking at heart rate and changes in physiology. But obviously, if the longer period of time you can get, I think it's the more beneficial.
Mm-hmm. And a lot of, like you were talking about, any of the analogs that we do here on the ground are just pale in comparison to the amount of time you can get up on the International Space
Yeah,
Station.
the space station is a scientist's dream, because, and you're talking months and months and months of being able to operate an investigation on orbit. And the cool thing about space station is it's analogous to a real laboratory. If you're a scientist, you don't do one experiment once and solve your hypothesis and come to a conclusion right away. You do that same experiment multiple times, and you manipulate all the different variables that you can. And the one thing you can't manipulate here on the ground is gravity. You can manipulate that in space station, and you're afforded the facilities and the timeline that you need to be able to repeat your experiment over and over again, so that you can arrive at a final conclusion and see if you test your hypothesis. So that's cool.
Very cool.
Yeah.
Okay, next question, please.
Mike?
Hi, I'm Mike. I was just wondering, about how far does the space station travel in one day?
I think it orbit the Earth about 90 times a day. Is that? Oh, no, I'm sorry, 15 times a day. So
it orbits about 15 times a day. Completes one orbit roughly every 90 minutes.
Every 90 minutes. Yeah. So that's about 17,500 miles an hour, I believe, is what the stats are.
So it travels about 17,500 miles an hour. Times that by 24, it's a little over 400,000, about 420,000 miles in one day.
Oof.
So pretty far. Next question, please.
Okay, Bennett?
Hi, I'm Ryan. I know that space travel can put the human body through a lot of stress. What kind of medical testing does an astronaut have to go through to be physically and mentally fit for a launch?
That's a good question. And I think there are standard tests that have been performed at NASA through the history of NASA, but it actually changes with the different launch programs. So for shuttle, when you're looking at shorter duration of maybe 2 weeks max for a flight, they're a little bit different than what they go through these days to be able to qualify for long duration stays on station, which could be up to 6 months. So for station, you really want to focus on history of kidney stones or renal stones. You want to maybe take a good look at their vision, make sure it's correctable if it's dropping off a little bit. Cardiovascular wise, their heart needs to be in really good shape. Muscles, they need to build muscle because all of these things are actually affected in that microgravity environment. For example, once you're on orbit and you're free falling and you're not using your postural muscles like you are to stand up all the time or walk around like you do here in gravity, those muscles start to break down. It's use or lose, right? So they start to atrophy. So one thing they need to be sure of is that they have really good muscle strength and tone and mass before they get up there. The other thing is cardiovascular wise. Once you're in space, all of the fluid tends to shift. It's because of surface tension and the fact that you're not using your legs anymore. All of the fluid in your body, the blood flow, tends to shift towards your central cavity in your head. So what that means is that the heart doesn't, the heart starts to just doesn't have to work so hard. So the cardiovascular system starts to get deconditioned. And the other thing is we've found recently that the vision starts to deteriorate on orbit. Not quite sure what's causing that, but it's happening more in the long duration astronauts. And with regard to kidney stones, you really don't want to be susceptible to that because when you're on orbit and you're not walking around a lot, you're not getting that impact on bone. Bone stays healthy because you are loading it constantly when you walk and run. In space, you miss that load, so you tend to start the bones use or lose, right? There's little cells in there that start to break that bone apart, and it doesn't remodel as quickly. So the breakdown of that bone goes through the cardiovascular system, gets filtered through the kidneys, and you could end up with that mineral in your kidneys and creating what's called the kidney stone. So you definitely don't want to be susceptible to that. So there are a few key things that we look at for long duration flight in the astronauts. But most of the time you hear our astronauts are really fit. They can run far and fast, and some can run faster than others. And it just varies by individual. But we try to meet the basics.
All right, thanks, Tara. Next question, please.
Okay, let's.
Hi, I'm Dan. Does debris from the spacecraft break down if it's released into space?
That's a good question. It depends on the type of debris. Although there's not technically oxygen in space, there's still atomic oxygen, and atomic oxygen is it's a little component, if you're familiar with it, that it just travels super fast, and depending on what the material is, that material could be subject to breakdown by just oxygen is just one example, but ultraviolet radiation, ionizing radiation, all the different types of little components that are still actually out there in space that are constantly bombarding the metal and the debris. And so we actually have an investigation on space station right now that's called MISSE, M-I-S-S-E, and it's a pallet just sitting externally on the space station that has all these different types of materials on it. And so what we use it for is we just subject all those materials to whatever is happening out there in space. So, and we get those samples back and we look at what happened here, and we look at them under microscopes, and we do destructive testing and all these other things. And so we get good input as to what materials actually are more susceptible to the damaging effects of the space environment. Some are more so than others. Some of those samples right now actually have the future of the spacesuit design samples on there, so that'd be kind of neat to get those results back. But so far, some of the investigation samples have come back on that. We've already made changes in some of our satellite material designs and solar array designs just based on the information we're getting back from these MISSE investigations. So it's a really good question, and that information is still going on. We're still trying to figure that one out.
All right, cool. Next question, please.
And Davis.
Hi, I'm Brian, and do you have to take into account the gravitational pull of the other planets and stars when you calculate the space station's orbit, or is it just so small that it doesn't have to be taken into account?
Right. So technically, space station is still in LEO, low Earth orbit, and so we're still technically under the effects of Earth's gravity, big time still, even though it's at the micro value, because we call it microgravity. So I'm not an orbital mechanics expert, but I don't believe they have to take into effect the calculation of other bodies. I think those are so far out and so far away from our low Earth orbit. I would imagine the further out you go, you do have to take these things into consideration. But with station being so still within the pull of gravity, I don't believe those are factors.
All right, next question, please.
All right, one from there. Go ahead.
Hello, I'm Annie. What would be some practical uses of microgravity that could be applied to everyday life on Earth?
So, geez, practical uses. Wouldn't it be fun if we could just take microgravity down here and practically apply it directly, kind of
fly around.
kind of fly around and translate? But indirectly, yeah, certainly. Some of the investigations I think that are happening with space station right now, right? It's a laboratory that investigates. You got to have why microgravity, why, and so practically speaking, in my mind, when I'm asked that question. I think people want to hear direct Earth benefits, but to me, it's partly about discovery too. Like we think we know who we are and how the body develops, but for example, how would a person develop? Think about how you're designed, your muscles, your bones, your brain, your eye shape, just the whole shape and way that we move is designed based on that gravity environment. So to me, it's about finding out what happens when you take that microgravity away. What happens when you have a developing living being in in a microgravity environment? What can we learn? How will it look different, or how will it function differently? Plants have evolved around microgravity, around the presence of gravity for millions of years, and they are very, very highly sensitive to it. So it's things like the fundamental discoveries, for example, fluid flow. Fluid behaves completely different in a microgravity environment, and I don't think, of course, I think the average person's not aware of it, but it behaves in ways that we've never seen on the ground. But by being able to collect that data, we can create models that benefit things here on the ground. For example, like cleaning up pollution in the soil, figuring out better ways to water our plants, because soil is a complex environment and fluid flows complex through that complex environment, and we actually don't have any clue as to how to predict fluid flow through soil. Imagine what that might mean for flooding, and just imagine what that might mean for crop production and maybe drought. So there are these fundamental discoveries that I think are cool just by being on space station, but what we really care about here are the things like cleaning up the soil pollution, the vaccine development for things like food poisoning. Another one that I think was really cool that came from space station was improvements on existing cancer treatment technology. You know, cancer, there's a way that you can treat cancer. It's been done since the 70s, and it's by taking these little micro balloons and filling them with anti-tumor drugs and actually injecting them right to the site of the tumor. And what some NASA scientists did was they thought, hey, we don't know what we don't know. What happens if we send a machine up to space station and use that microgravity environment to see how we can manipulate fluid mixing in space and maybe create improvements on these little micro bubbles? And that's called microencapsulation. And so they did. They sent a machine up to space station, made some micro balloons, sent them back to Earth, investigated them, found brand new properties of these things, and were able to, in their own laboratory testing studies, show an improvement in rat prostate treatment in cancer. So it was, I think, by 60% improvement. And so this team has now gone off and patented a machine that could do the same thing. It could actually replicate what was done in a microgravity environment. And now they're about to go through, they're raising funds right now to go through clinical trials at MD Anderson, which is a major cancer center. But it's things like we don't know what we don't know, and sometimes you do it because of that. Sometimes you do it because we want to improve fluid flow predictions in space because it helps us design better fuel tanks, but it also helps us to clean up our soil. So for me, it's just fundamental discovery, and you can take just about every fundamental discovery and apply it to your everyday life. And it's just, the list is long, but it's a good list.
It is incredibly long.
Yeah.
All right, next question, please.
Okay, Silky.
Hi, my name is Meredith, and I was wondering that if there was like a natural disaster or a nuclear war or something to happen here on Earth, and everyone on Earth was killed, what would the astronauts that are in the space station supposed to do?
I think they'd have to figure that one out. If no one was left on the planet, do they want to come home?
Kind of be left on their own
They
for
kind
that
of,
one.
yeah.
We don't have any protocols like that in place.
Although I think the return vehicles, the Soyuz up there, could technically send them home, right? Even if no one was manning the.
They could, but the return vehicles have a on-orbit lifetime of only about 200 days.
So they'd have to figure out fast
they
what
could
they.
either stay on board the station, which has limited consumables, or come back down to the Earth.
And so then I guess it's up to your imagination as to what happens next.
It would be a difficult choice.
Yeah.
All right, next question, please.
All right. Isabella.
Hi. Is it true that flames become spherical in microgravity?
Yeah, it is. That's a good question. There's an investigation that actually they did part of it this week. There's lots of combustion and flame experiments in microgravity, but this one in particular is called SLICE, SLICE, and you can look it up at nasa.gov if you're interested. I think we might have even written a story on it. But yeah, because there's no gravity. So when you light a flame in gravity, right, the hot air will rise to the top. The cold air will just start. That's how you circulate. The hot air rise to the top, and then the cold part of the flame will just get heated and move to the top. But without that's part buoyancy and part convection. But without gravity, and you get this microgravity environment, now you don't have buoyancy or minimal buoyancy. You have minimal convection. So the flame tends to just stay in a spherical ball, just attracted to itself, rather than being able to have that hot air rise up in the way that you see it here on the Earth. So in space, you don't get that hot air that's rising up. The hot air, the hot part of the flame, just stays in a ball to each other. It's where it's happiest. Its molecules are more efficient. And so yeah, everything that we use in space that has anything to do with a flame has to be treated differently. Every kind of not only experiment but system that might use that. So the investigation that happened this week is actually looking at something called flame detachment. How is a flame truly? They're getting the characteristics. We've got these nice pictures that you alluded to, but we're truly trying to understand, really zone in on the characteristic structure of a flame in microgravity and gain more information of that. Not just that, but also the amount of soot that's produced in microgravity from a flame. And so the combustion effects of fire in space is such that it produces more soot than a flame would produce on the ground. And that was a pretty interesting finding, because that means a lot of different things to be able to detect smoke instances on orbit. Our smoke detectors would have, are designed to specifically address the soot formation in a way that we have never developed here on Earth. So yeah, flames are just one thing that behaves differently thanks to the minimized or the masked buoyancy and convection effects in microgravity. Okay.
All right, and I think we have time for one more question, real quick.
Okay.
Hi, I'm Erica. I was just wondering about how much force is needed for a spacecraft to break through the atmosphere.
I don't know numbers exactly, but it's my understanding it would have to be a velocity and an angle great enough to be able to create enough energy to be able to escape Earth's gravity, which is what, guys, 9.8 meters per second squared? Do you know any numbers? Hardcore numbers?
I don't know exact numbers. A lot of times people confuse it with escape velocity.
Yeah.
Which, if that was true, you'd have to be going about 25,000 miles an hour, but that's if you had no more propulsion behind you.
Yeah.
So it's actually a fairly difficult question, but if you just look at the speeds that our spacecraft attain, they get about 17,500 miles just to maintain an orbit. So if you continued on that path, you could feasibly escape Earth's gravity at that speed, as long as you still had propulsion pushing you outwards.
Yeah, right. And I would imagine at the level of launch, if you're talking about launch, it probably is vehicle dependent too.
Mm-hmm.
So.
All right. Well, that'll about wrap it up with us today. We really want to thank you guys for your great questions.
Yeah. Thank you. It was good talking to you guys.
And it was great talking to you guys. Thank you.
Thank you.
Thank you.
Thank you. Bye.
Thanks. Fill the thrill.